Newton's method. Suppose we wish to find the number r at which the function f of x crosses the x-axis. This number r is often called an x-intercept or a root or a zero. And it is the solution to the equation f of x is equal to 0. So if r is the solution, then we know that f of r is equal to 0. So this is why it is often called a zero of the function. It's the number that you plug in to make the function equal 0. Now, if your function is a simple function, like a polynomial or particularly a quadratic function or a linear function, finding the x-intercept is really simple. We can usually solve a simple equation by factoring or the quadratic formula or some other means. But if your function is more complicated, it is often very difficult to solve for the zero of the function. So we're going to create a process that will allow us to approximate this solution. So if r is the point on the x-axis at which the function crosses it, let's suppose that we can guess approximately where this number is, and we'll call that guess x1. Now, x1 is not equal to r, and you can see there's a substantial distance between r and x1. But if we go to the point on the function at x1 and draw the tangent line, I want you to notice that the tangent line will intersect the x-axis closer to r than our starting point. And so this number here we are going to call x2. And x2 is an improvement on x1. Now, how do we find this number x2? Well, let's first remember how to find the equation of a tangent line. So we know to find this equation, y minus y1 is going to equal m times x minus x1, where the point x1, y1 is the point of tangency, and m, the slope, is the derivative of the function evaluated at x1. Now, let's also keep in mind that y1 can be viewed as f of x1. So if I plug these quantities in, I have y minus y1, which I'm going to write as f of x1, is equal to the slope, which is f prime of x1, multiplied by x minus x1. So this is the equation of our tangent line. And if we want to know where that tangent line intersects the x-axis, which would be the x-intercept, remember, to find an x-intercept, you need to let y be equal to 0. So if we substitute y equals 0 here, we get 0 minus f of x1 is equal to f prime of x1 times x minus x1. And now I just want to solve for x, right? The solution x here is going to be the x-intercept. So to do this, I'm going to divide both sides by f prime of x1. And what happens here is these cancel out. And so on the left-hand side, I have negative f of x1 divided by f prime of x1. And on the right-hand side, we have x minus x1. Keep in mind, we are trying to solve for x here. So all we need to do next is just add x1 to both sides. And when we do that, we're going to get x is equal to x1 minus f of x1 divided by f prime of x1. And this is the x-intercept of our tangent line. So it means that this is x2. So we now know what x2 is. Okay, and I can write that down. So we know that x2 is equal to x1 minus f of x1 divided by f prime of x1. All right, and so x2 is closer to r, right, than x1 was. So x2 is an improvement. But x2 is still pretty far from x1. So how do we improve that again? Well, we do the same process. So if I go up to the function at x2, and if I draw the tangent line at x2, notice that that tangent line will intersect the x-axis here, and we'll call this point x3. Now, how would you get x3? Well, you would get x3 exactly the same way that you got x2. The only difference is you would find the equation of the tangent line at x2, right? So your point of tangency wouldn't be x1, y1, it would be x2, y2, and your slope would be f prime of x2. So the equation of your tangent line, everywhere you see an x1, you're going to put an x2. And then when you set y equal to 0 and you solve for x, again, you will get this same formula, but everywhere you see an x1, you will have an x2. So what that means is that x3 would be x2 minus f of x2 divided by f prime of x2. And we can see on our picture here that x3 is indeed closer to r. But, of course, we can get even closer. So there's where x3 is. But if you took that number x3 and went up to your function and drew a tangent line at that point, and then found the point of intersection with the x-axis of that tangent line, you can see that that number, which we would call x4, would be even closer. And you would find x4 in exactly the same way. So x4 would be x3 minus f of x3 divided by f prime of x3. And basically, you can keep doing this, and every time you do one more of these, your approximation gets that much better. So this leads to a formula that says if you want x n plus 1, all you need to do is take xn minus f of xn divided by f prime of xn. And this formula is the formula that we refer to as Newton's method. So in our first example, we want to use Newton's method to approximate the solution, correct to 6 decimal places, to the following equation using the given initial approximation. So we wish to solve this equation, 2x cubed minus 3x squared plus 2 is equal to 0, and our initial approximation is that it is -1. So here is Newton's method. Now let's remember, in order to use Newton's method, you have to identify your function f of x that is set equal to 0. So in this case, it's pretty easy to see that this is your f of x. So we have f of x is 2x cubed minus 3x squared plus 2, and we're trying to figure out when is that equal to 0. So to apply Newton's method, we need f prime. So f prime of x here is 6x squared minus 6x. And then all you have to do is plug in to Newton's method. So we know that xn plus 1 is equal to xn minus f of xn is basically just f of x with an xn here. And so that is going to be 2 xn to the third power minus 3xn to the second power plus 2 divided by, and then f prime of xn is basically just xn plugged into your derivative. And so that will be 6xn squared minus 6 times xn. So this is the formula for Newton's method. Now what we need to do is use this formula to get the approximation correct to 6 decimal places, understanding that our first guess, which was given, was -1. So to get x2, what we need to do is plug x1 into our formula. So we're going to plug -1 in for x1. So if you want, first of all, it will look like this, and you don't have to actually write down this step, but this is the formula used precisely. And then we know that x1 is -1, so this will be -1 minus 2 times -1 to the third minus 3 times -1 squared plus 2, and then that part is over 6 times -1 squared minus 6 times -1. And so clearly finishing this up is a calculator problem, so I'm going to go ahead and bring in that approximation. And so you can see what we get here is -0.75. Now let me explain the way I did this on a calculator here. The easiest way to do it is to enter your original estimation. So I just hit -1 and enter. And then you can see I typed in the formula here, but rather than putting in -1, I simply put in the answer function. So notice that we have the answer minus 2 times the answer to the third power minus 3 times the answer to the second power plus 2 divided by 6 times the answer squared minus 6 times the answer. That is exactly this formula. And that produces -0.75. And so that is x2. Now to get x3, we are going to plug x2 in. And so it would be x2 minus all of this, right? So basically just do the same thing we just did, but we're using x2 instead of x1. And when you go to actually type that in, those x2s would be -0.75. So this is the last time I will write this, but it would look like -0.75 minus 2 times -0.75 to the third minus 3 times -0.75 to the second plus 2 divided by 6 times -0.75 squared minus 6 times -0.75. And when you plug that into your calculator, you get -0.682539, etc. And that is x3. And so we're just going to repeat this process. And so I'll bring in the next few calculations. So we're going to have a calculation for x4, a calculation for x5, and then let's see where we're at that point. And so here they are. So if we look at 6 decimal places, you can see that x4 is approximately -0.677675, and 6 decimal places on x5 would be -0.677650. So notice that they're still changing. So we need to do this at least one more time. So let's bring in the approximation for x6. And what you can see now is that if we go out to 6 decimal places, we are getting approximately -0.677650. So notice that those 6 places are unchanged. So once those 6 places do not change, you can go ahead and round. Now, I actually did make a very slight error here, because if you were to round the 6th place here, this would change this 0 into a 1. So let's go ahead and account for that. And the same thing would happen here. This 6 would change that 0 into a 1 as well. And so we can now say that our solution is approximately negative 0.677651. And of course, you can check this by simply plugging that number into the original function, and you should see that the output is very, very close to 0. So in our next example, again, we want to use Newton's method to approximate the solution correct to 6 decimal places to the following equation using the given initial approximation. So notice this time the equation is x to the 5th equals x squared plus 1. Now to use Newton's method, you have to have your function set equal to 0. So the first task is to simply identify what is the function that we're going to use in the formula. So of course, if we have x to the 5th power equals x squared plus 1, what you can do is subtract x squared and subtract 1 from both sides, and that will give you x to the 5th minus x squared minus 1 is equal to 0. And this is our f of x. So now to apply Newton's method, we just need to find the derivative. The derivative here is 5x to the 4th power minus 2x. And then if we simply plug that into our formula here, we get xn plus 1 equals xn minus f of xn will be xn to the 5th power minus xn squared minus 1. And then divided by f prime of xn is 5 times xn to the 4th power minus 2 times xn. And our first approximation here is 1. And so let's go ahead and go through the process on the calculator to get the next several iterations of this process. And so here they are. And I want you to notice that it took us 6 times going through the process. And if you look at x7 to 6 decimal places, you will notice that it is the same as x6 to 6 decimal places. And so what is the solution approximated here? So let's go ahead and go out to that 6th decimal place, which is right there. And we're going to say that this solution is approximately 1.193859. In our next example, it says, find correct to 6 decimal places the solution of the equation cosine of x is equal to x. So just like before, if you're going to use Newton's method, the first thing you need to do is get a function set equal to 0. So there's a couple of different ways to do this. You can either subtract x or you can subtract cosine of x. And so for this one, I'll just subtract cosine of x. It does not matter which side you get your variables on. And this will be our function f of x. Okay, so next, of course, we need f prime of x. The derivative is 1 minus the derivative of cosine, which is negative sine. And that, of course, is 1 plus sine of x. So again, our function f of x is x minus cosine of x. And now f prime of x is 1 plus sine of x. And Newton's method will give us xn plus 1 is equal to xn minus f of xn. So we are plugging xn into the original function, and then divided by f prime of xn. And so here is our formula. But now we come to the part where we have to come up with the initial approximation. So if this x1 is not given to you, how do you choose that? Well, one thing you can do is you can draw a graph of the function cosine of x and the function x to try to guess to see approximately where they intersect each other. So cosine of x is a graph that looks like this, more or less. And the function y equals x is the line that comes straight through like this. So we can see that those two functions intersect here, and we know that this value for cosine is pi over 2. And pi over 2 is about 1.57. So where are they intersecting? Well, I think a very reasonable first guess here would be to just say x1 is equal to 1. Now, you can also use a graphing calculator to graph these functions to get that initial approximation. But honestly, that kind of defeats the purpose of Newton's method, because if you're using a graphing calculator, most graphing calculators will give you the point of intersection. And so the whole point with Newton's method is not just to find the solution, it's to understand the process. Because if all we care about is the solution, we have technology that will give us these solutions very easily. So we are emphasizing the process here. So let's go ahead with that guess. So x1 is equal to 1. And now let's get our next few iterations of that. And hopefully by the time we get to x6, we will have a 6 decimal place approximation. Now, one last thing I need to say before you plug this into your calculator, it is very important that your calculator is in radian mode, okay? It will not work if your calculator is in degree mode. We do not use degrees in calculus, so we need to make sure that our calculator is in radian mode. Now, let's go ahead and get those approximations. And actually, you can see that by the time we get to x5, these 6 decimal places here are unchanged. So we didn't even need to go to x6 in this case. So we can say the solution here is approximately 0.739085. So again, when you approximate, you go to the 6th decimal place, draw a line there, and then check the number to the right, because that is going to affect the rounding of the number to the left there. Now, of course, the number to the right here is a 1, so that doesn't change the 5 in this case. In our final example, we want to use Newton's method to find the 6th root of 2 correct to 8 decimal places. So first of all, let's assume that x is equal to the 6th root of 2. The whole point of this problem is that we don't know how to take a 6th root without a calculator. So what I'm going to do is transform this equation by taking both sides of this equation and raising it to the 6th power. Now, why would I raise it to the 6th power? Well, it's because when you take a 6th root and you raise it to a 6th power, it is going to cancel that radical. And so we end up getting x to the 6th power is equal to 2. And this is the same as x to the 6th power minus 2 is equal to 0. And just like that, we have our function f of x. And now we can apply Newton's method, so we need the derivative, which of course is 6x to the 5th power. And then Newton's method says that xn plus 1 is equal to xn minus f of xn divided by f prime of xn. And so in our case, xn plus 1 will be xn minus xn to the 6th power minus 2 divided by 6 times xn to the 5th power. And then we have to pick an initial guess. Well, what do we know about 6th roots? Probably not much, but you probably know the 6th root of 1 is 1. And you may or may not know this, but the 6th root of 64 is 2. So if we're taking the 6th root of 2, 2 is much closer to 1 than 64. So I'm going to once again go with an initial approximation of 1. And now let's run that through the process to get our approximation. And this time I'm going to skip all the calculator steps, but let's go ahead and run it through to see what we get. And after doing this 4 or 5 times, we come up with an approximation of 1.12246205. Remember, we're going to 8 decimal places this time, and that 8th decimal place is right here. And so this is our approximation. Now, of course, you can check this approximation by just taking the 6th root of 2 on a calculator, but I will leave that to you as an exercise. And that concludes this video lesson.